core mission here is to totally demystify how AI actually learn to understand and generate language. And by the time we wrap up the session, you, our listener, are going to be able to do 3 very specific things. Play them out. First, you'll understand the foundational mechanics of sequence-to-sequence models. Right? Second, you'll grasp exactly why this concept called attention was just a revolutionary breakthrough in overcoming the limits of early AI. Yeah. And third, you'll see how these exact architectures were adapted to power the dynamic chatbots that you probably, interact with every single day. To get there, let's anchor this to what you might already know, especially if you've been following along with our earlier materials. We explored long short-term memory networks, LSTMs, and gated recurrent units, GRUs. Yeah, how do you map an input sequence to an entirely new output sequence? Exactly, that is the metacognitive question here. And that's the exact problem researchers faced around 2014. The solution came in the form of 2 groundbreaking papers, one by Cho and colleagues, and another by Sutskever and colleagues. Okay, they introduced this dual LSTM setup, which they called an encoder-decoder model. And this is the bedrock of sequence-to-sequence, or C2-sec learning. Okay, let's unpack how a dual LSTM actually functions. You basically have one neural network acting as the encoder, and then the totally separate network acting as the decoder. Yeah, that's the architecture. So the encoder takes your input sequence, let's say it's an English sentence you want to translate, and it processes it one token or word at a time. It updates its internal state with every new word it reads, kind of building up a mathematical representation of the sentence. And it keeps reading until it encounters a very specific token. The sequence marker. Right. Exactly, the EOS token. And that EOS token is the trigger. Yeah. It basically tells the encoder, okay, the sentence is done, but here's where it gets wild to me. Yeah. Once it hits that end token, the encoder takes everything. It just all that context, all those words, all that grammatical structure, and it just compresses it into a single fixed-length vector, which we refer to as the final hidden state. Let me try to put a visual on this for you listening. It's like taking an incredibly complex, nuanced legal document, feeding it into a machine, and having the machine spit out a single dense barcode. A barcode! That's a good way to look at it. And that barcode allegedly contains the meaning of the entire document. That is a highly accurate analogy, actually. That vector, your barcode, is a dense mathematical nugget of context, and that is where the handoff occurs. The encoder passes this final hidden state over to the decoder network. So the decoder takes this barcode, and its only job is to generate a brand new sequence, like, say, a French translation. Exactly, and to do this, at every single step of generation, the decoder is looking at 3 distinct pieces of information. Okay, what are they? Well, it looks at that final hidden state from the encoder, the barcode. Right, it looks at the specific token it just generated in the previous step, and it looks at its own previous hidden state. It uses those 3 inputs to calculate the probability of what the next word should be. Wow. So it predicts the next token, and the next, until it finally decides the translation is complete and outputs its own EOS token. If you're listening to this, I want you to pause for a second and just think about the structure we just described. Why is having 2 separate networks, an encoder and a decoder, connected by a single vector, such a massive leap forward from the old ways of doing things? The real breakthrough there is flexibility. I mean, in older models, mapping sequences was incredibly rigid. But here, the input sequence and the output sequence do not have to be the same length. Right, mathematically speaking, m does not equal n. Exactly. Which is absolutely essential for natural language. You might translate a 5-word English sentence into, an 8-word French sentence. Or a 10-word question into a 3-word answer. Yeah. The C2-sec model handles this so elegantly because everything routes through that central bottleneck, the final hidden state. The decoder isn't tied to the length of the input. It just unpacks the meaning from the vector until it naturally concludes. And both of these networks are trained simultaneously. The optimization algorithm is constantly tweaking the internal weights of both the encoder and the decoder to maximize the probability of the correct output sequence given the input sequence. They're essentially solving for a log likelihood function. Right. They want the mathematical probability of producing the correct translation to be as close to 100% as possible. But wait, this brings us back to that bizarre quirk I mentioned at the very beginning. This detail from the Sutskever 2014 paper. Oh, the sequence reversal. Yes. The researchers found that the model was struggling to optimize, so they applied a strange hack. They took the input sequence, the source sentence, and fed it to the encoder backward. Yeah, it dramatically improved the model's performance, which honestly confused a lot of people initially. I'm still slightly confused by it. Why on earth would reading a sentence backward help a machine translate it better? Human translators certainly don't read sentences backward. It comes down to establishing short-term dependencies for the optimization algorithm. Think about the structure of translation. When you feed a sentence forward, A, B, C, the first word of the English sentence, A, is processed first. Okay, making sense so far. But by the time the encoder gets to the end of the sentence and passes the hidden state to the decoder, that first word is buried deep in the math. Oh, but the decoder usually needs that first English word to figure out the first French word. Ah, I see. So there's a massive mathematical gap between the first input word and the first output word. Exactly. By reversing the source sentence feeding it C, B, A, the first word of the English sentence is now the last thing the encoder reads. So it's fresh. Yes, it is fresh in the hidden state. It is physically right next to the first word the decoder needs to produce. It acts as a bridge, making it vastly easier for the model to get started and figure out the mapping. It's a brilliant, almost like mechanical workaround for a digital memory problem. But let's push this architecture to its limit for a second. Let's do a quick formative check-in. Okay, I want you to visualize this encoder-decoder process we've been talking about. You have the encoder reading a text, compressing it into a single barcode vector, and the decoder unpacking it. Now imagine you are asking this model to translate a highly complex, highly nuanced 50-word sentence. That's a lot of words, right? What happens when you try to cram a massive paragraph into one single fixed-length final hidden state vector? The math simply breaks down. The model suffers from severe truncation. Exactly, it's the bottleneck. A single vector just does not have the capacity to remember a long sequence perfectly. The model literally starts forgetting the early observations because the information capacity of that vector is, well, it's finite. The longer the sentence, the worse the basic Scikit-learn model performed. It was hitting a wall. But in late 2014, Badano and his colleagues proposed a radical, elegant solution. Oh, I love this part. They realized the problem wasn't the encoder or the decoder. The problem was forcing the encoder to compress everything into one single vector. So they asked, what if the encoder didn't output one vector, but a whole sequence of vectors, which we call annotation? Yes, annotation. To really differentiate these two approaches, think of the basic C2SEC model as closed book translation. Okay, read an entire page of a book, snap the book shut, and try to translate the whole page entirely from memory. By the time you get to the fourth paragraph, you've forgotten the specific phrasing of the first. It's an incredibly stressful, inefficient way to translate. Seriously. It forces the model to rely entirely on memorization rather than translation. Exactly. But this new approach from Badano, which they named the attention module, is like keeping the book open. Yes, it allows the translator, the decoder, to keep the original text on the desk, point its finger at specific source words, and focus on them while it is actively writing the corresponding translated words. The mechanism of attention changes the context vector from something static into something dynamic. For every single word the decoder generates, it calculates a brand new context vector. Right. It looks at all the annotations the encoder produced one for every word in the source sentence and decides which ones are most mathematically relevant to the specific word it's trying to predict right at that millisecond. Let's walk through a work example step by step so we can actually see the gears turning here. Okay, let's do it. Let's take a simple phrase. We are translating the English phrase, the cat is black, into the French phrase, le chat est noir. Okay, so the encoder processes the source. It creates an annotation vector for the, another for cat, another for is, and another for black. Now the handoff happens, and the decoder needs to output its very first word. To do this, it relies on an alignment model. And what exactly is the alignment model doing under the hood? It's actually a secondary, smaller neural network working inside the decoder. Its job is to measure the similarity between the decoder's current state and every single one of those input annotations. It scores them based on relevance. So it's scanning the source and asking, out of the cat is black, which of these words should I be paying the most attention to right now to get the first French word? Yes, and it expresses that relevance using a softmax probability distribution. Oh, softmax. Yeah, softmax is just a mathematical function that takes a bunch of numbers and turns them into probabilities that all add up to 100%. So, for the first French word, the alignment model might assign a 90% probability to the English word the, okay, a 5% probability to cat, and tiny fractions to the rest. It's like distributing its attention budget. Precisely. It uses those percentages as weights. It multiplies the annotations by those weights and sums them up. Because the has a 90% weight, the resulting custom context vector heavily favors the mathematical representation of the. The decoder uses that highly focused vector to confidently output le. And the brilliance of this is what happens on the very next step. Oh, absolutely. So the second word, the attention completely shifts. The alignment model recalibrates. It looks at what it just did, looks at the source again, and this time puts like 95% of its weight on the word cat. Right. The decoder receives this new context vector and outputs chat. It is literally moving its mathematical attention across the input sequence as it writes the output sequence. And we should note, in modern applications, the encoder is usually a bidirectional LSTM, meaning it reads a sentence left to right and right to left simultaneously. Yes. So when the decoder is focusing on cat, the annotation for cat actually contains some mathematical context about the word black that comes after it. Oh wow. This makes the attention incredibly rich, allowing the model to handle complex grammatical inversions between languages. The theory sounds airtight, but did keeping the book open actually translate to better results? They benchmarked this using the WMT14 English to French translation dataset, evaluating it with a metric called a BLEU score. And higher is better. Higher is better. The baseline for a long time was a statistical, rule-based machine translation system called Moses. It was heavily engineered by linguists and scored a 33.3 on the BLEU scale. Okay. Then, Sutskever's massive basic CKey-sec model, the closed-book version we talked about first, was tested. This was a behemoth, 5 LSTMs, 384 million parameters. Wow! It pushed the score to 36.5, a solid improvement over the rule-based system. But once the attention mechanism was fully integrated and refined, the architecture absolutely exploded in capability. Our sources point out that by 2019, systems like DeepL utilizing advanced attention architectures hit a BLEU score of 45.9 on that exact same benchmark. That is a huge jump. Yeah, it wasn't just an incremental update. Attention removed the fundamental memory bottleneck. It allowed neural networks to process language dynamically in a way that mathematically mirrors human cognitive focus. Which opens up an incredible, almost philosophical question. If a model can learn to translate English into French by mapping one sequence to another using attention, could it translate a question into an answer? That thematic leap is exactly what researchers Oriol Vignoles and Kwok Lei explored in 2015. They realized that sequence-to-sequence with attention isn't just a translation engine, it is a universal sequence mapper. So instead of the first input being an English phrase and the target output being a French phrase, the first input is just a human phrase, and the target output is the logical reply to that phrase. You're mapping dialogue. Exactly. They took the exact same encoder-decoder framework and applied it to conversational modeling. Which is wild. This was radical because early chatbots were entirely rule-based. They relied on, brittle decision trees. If the user types the exact word refund, output script Y. If they use a word not in the tree, the bot crashes and says, I do not understand. But a neural approach throws away the decision trees completely. It relies purely on data and probability. And the sheer scale of the training data Vignoles and Lei used is staggering. Oh yeah. To teach the model how to converse, they used two main datasets. First, the open subtitles dataset, movie dialogues. We are talking about 932 million tokens. They forced the model to read nearly 1 billion words of movie script so it could mathematically model the natural rhythm, colloquialisms, and flow of human back and forth. And the second dataset was incredibly specific. It was an IT help desk troubleshooting dataset. About 30 million tokens of actual humans chatting with tech support. Right. Let's walk through exactly how the model performed after training on this IT dataset, because the mechanism here is fascinating. Let's say a human types the prompt. I'm using Linux. Okay, so the machine's encoder reads that sequence and creates the hidden states. The decoder, utilizing its alignment model and attention mechanism, calculates the probabilities. It recognizes the context, it maps the sequence to the high-dimensional space of IT troubleshooting, and it begins generating a response token by token, and it outputs, please open terminal and run the below commands in one computer, sudo apt-get update. Yeah. The human then types done, and the machine replies, let me try connecting now. And here is the critical point to understand. The machine is not copy-pasting a pre-written script from a database. Right. There is no file labeled Linux troubleshooting script A. It is generating these sequences word by word from scratch based purely on calculating the highest love likelihood of the next word given the previous words. Wow. It absorbed the context of troubleshooting Linux from the 30 million tokens and generalized that statistical knowledge to dynamically respond to a prompt it had never even seen before. To prove this wasn't just a fluke, the researchers benchmarked their neural conversational model against Cleverbot. For those who don't remember, Cleverbot was considered a highly advanced chatbot at the time, but it relied heavily on finding previous similar conversations rather than generating from a deep neural state. They subjected both systems to 200 questions and had human judges rate the responses blindly. The traditional Cleverbot scored a 60. Okay. The neural model scored a 97. It crushed it. Totally crushed it, because Cleverbot's rigid structures broke down the moment a user introduced unseen context, whereas the neural model used its attention mechanisms to dynamically map the user's current sentence to the historical context of the chat. The neural model's ability to maintain context over multiple turns of conversation made it feel vastly more fluid and intelligent. And this is a massive but. When you see a machine giving you a highly contextual, helpful answer about Linux, or keeping track of conversation over several turns, it is incredibly easy to think, wow, this thing really understands what it's talking about, and have a persona. This brings us to a major common misconception that we really need to explicitly address. It is perhaps the single most common misunderstanding among learners and the general public regarding AI. We naturally anthropomorphize the model. Right, we project human consciousness and intent onto it. But the model does not understand anything in the human sense. It does not have an identity. It is simply a probabilistic engine minimizing perplexity. Let's define perplexity quickly. Perplexity is just a measure of how surprised the model is by a sequence of words. The model's entire goal during training is to adjust its internal weights so that the actual human responses in the training data have the lowest possible perplexity, meaning they are highly predictable. Exactly. It is just trying to predict the most mathematically likely next word based on the patterns it saw in a billion words of subtitles. And the Vinyals in the paper provides the absolute perfect, hilarious proof of this limitation. They published a failure from the model trained on the movie subtitles that proves it has no actual self-awareness. I love this example. A human tester asked the machine, "What is your job?" And the machine replied, "I'm a lawyer." A perfectly reasonable, syntactically correct sequence to generate in response to that specific arrangement of tokens. But just moments later, they asked it a semantically identical question. What do you do? And the machine confidently replied, "I'm a doctor." Yeah. Pause and think about this for a second. Why did the model completely contradict itself in the span of 2 questions? Because it has no persistent memory of an identity. It isn't checking a central database under the file name my identity before it speaks. Right, when you ask, "What is your job?" The specific arrangement of those tokens triggers a mathematical pathway through its neural network that leads to lawyer based on its training weights. And when you ask, "What do you do?" that slightly different arrangement of tokens triggers a completely isolated pathway that happens to lead to doctor. It is just reacting in a vacuum to the prompt. Building a consistent personality or persistent state into these models became the next great frontier. Because without it, you have a brilliant conversationalist who suffers from total amnesia every time you hit enter. Yeah, exactly. All right, let's bring this all together and synthesize this learning journey. We started by breaking down the basic encoder-decoder architecture, C2Sec. We saw how it used a final hidden state to compress variable long sequences into a single vector, overcoming the rigid rules of older models. Then we identified the fatal flaw of that approach, which was the memory bottleneck for long sequences, the closed-book translation problem. We saw how Boudinot and others solved that bottleneck with the attention mechanism. By outputting a sequence of annotations and using a softmax alignment model, they allowed the decoder to dynamically weigh different parts of the input sequence. They kept the book open. And finally, we saw how Vinyals and Le transfer that exact same C2Sec with attention technology from translating languages to mapping dialogue, giving birth to the modern neural conversational chatbot. And here is the real-world application for you. This isn't just a history lesson about 2014. Every single time you use a modern AI writing tool, every time you argue with a smart customer service bot, every time you use auto-translate on your phone, you are interacting with the direct descendants of these specific breakthroughs. The underlying DNA of Scikit-learn attention is running in the background of your digital life right now. They laid the architectural tracks that almost everything in modern natural language processing is currently running on.